Okay, so in this example, we are going to be trying to compute the confidence interval for a mean with sigma unknown. This is very similar to the example that we did in class where we tried to compute the confidence interval for the mean with sigma known. If we don't have sigma, as we're not going to by the title of this, clearly sigma is going to be unknown in this case. So if we don't know sigma, the suggestion was to use S, which is the standard deviation of the sample, instead. And so later on, when we try to compute the margin of error, which looks like our critical value z sub alpha over 2 times sigma over the square root of n, here's going to be our formula for the margin of error, we don't have this piece anymore. And so instead, I'm going to replace it with s over the square root of n. And unfortunately, one of the issues that this does is it means that this is no longer going to follow a normal distribution. So what we previously called our z-score, being a position somewhere on our normal distribution, turns out that normal distribution isn't normal anymore. We are going to have a curve. It's going to look vaguely like a normal distribution, but it's going to be instead called a t-distribution. So it's going to look like a normal distribution. It's the distribution of all our possible x-bar values here. And again, we're trying to find the value of mu down here. But this is going to be what's called a t-distribution instead. And we mentioned in class sort of the history of this, that it dates back to a guy that worked for the Guinness company that makes beer in Ireland. He was a statistician that developed this essentially so that they could compute interesting statistics to measure how impressive various feats were that they were going to put in their Guinness Book of Records. So what is the difference between, between a normal and a t distribution? The difference is basically this. For a t-distribution, there's actually a bunch of them, and they take the size of the sample that was used into account. So essentially, I'll draw a picture here. This is kind of what you might get for a t-distribution with n equal to some small number, let's say 5. So a small sample size. The main feature of it that differs from a normal distribution is that the middle region is going to be a bit lower and the tails are going to be a bit fatter. So as we increase the sample size, what's going to happen to the shape of this is we're going to get a different t-distribution that's a bit lower in the tails and higher in the middle. Winds up starting to follow a shape like this. So this might be one where n is equal to, I don't know, maybe 100 now. And so again, you can see the peak is getting larger and the tails are kind of getting skinnier as the sample size increases. Well, eventually, if you let n get really large, we will approach a shape that looks like this one. And this last shape is the normal distribution. So basically, as you increase the number of the value of n in your sample size, you will get a distribution that approaches a normal distribution. For us, basically, once our sample size reaches, so n greater than 200, we're going to just treat this t-distribution as a normal distribution. It's going to be so close. This is actually what we're going to use. Let me not move my video here. that third table that I gave you guys the other day, let me get these back in order here. Sorry, I apologize. Bottom table, A3, here we go. Here's the t-distribution that I'm talking about. On the left, we have these degrees of freedom. Those correspond essentially to the value of n. There's just one thing that we need to keep in mind. So we're going to come back and look at this table in just a minute, but that's what we're going to be doing for problems of this nature. So we need to know which, so we want to know which t-distribution to use. And to do that, we need to know the degrees of freedom. Which I will abbreviate as DOF. And the degrees of freedom is just going to be equal to n minus 1. You'll remember that n minus 1 showed up in the denominator of our standard deviation way back in chapter 3 when we were computing the standard deviation of a sample. It was different from the standard deviation of a population where the denominator was a capital N, and I mentioned at the time that it had to do with something called degrees of freedom. I'm not going to go into that detail again, but this is the idea. Every value of the degrees of freedom corresponds to one of these curves up here, a slightly different shape. And so, for example, let's do a problem. If I tell you that we wind up having a sample that is of size, if our sample has size of n equals I don't know, 35. Then the degrees of freedom is just one less than that number. So it's going to be 35, oh come on pen, 35 minus 1, which is 34. And on our table over here, when we got to that problem, what we would use is this row labeled 34. That is our degrees of freedom. These numbers only in this row would be the relevant numbers to our problem. And we'll talk about exactly how to use them going forward, but basically we've used this table in the past where we look at the confidence interval and immediately above that we have the number that corresponds to the what we call the critical value of the problem. The same thing that played the role of that z sub alpha over 2 that I wrote in our margin of error. You may recall from class a 95% confidence level wound up having a critical value of 1.96. In this problem, if we were doing the same type of thing, a 95% confidence level, the critical value that we would use isn't going to be the 1.96 because that's the one in the row labeled z where we're treating it as a normal distribution. We're using a t-distribution with degrees of freedom equal to 34, so this is the row we'd be using, and there is our confidence level, so this number's sitting right here, boom, 2.032. That is the number we would use for our critical value for that particular problem. So this is how we'll wind up using this table to figure out exactly what we're looking for. Okay, so let's go back to our writing over here. Okay, here's that problem. That's how we'll wind up using that table. So we will use the row labeled 34 of table A3 to find the critical value. And the only thing that's going to be different about these problems than what we were going to be doing or what we did previously is We're no longer using a z-score, so we're going to call this critical value t sub alpha over 2 instead of z sub alpha over 2. But this is going to be the only real difference between the problems that we did before and the problems that we're going to do here. So, with this in mind, I'm going to lay out our procedure for these types of problems. And it's the exact same 5 steps that we've talked about previously on those other problems. So, step number one is find the point estimate. That point estimate is still x bar, just as before. The second step is to find the critical value. And we just mentioned how we're going to do that. So find the critical value. That critical value is going to be t sub alpha over 2, and it depends on the given confidence level. For example, 95% confidence, 99% confidence, etc. So the given confidence level and degrees of freedom, which is just, again, one less than our sample size. In the third case, for the third step, we will find the standard error. And as I mentioned before, normally this is sigma over the square root of n, but in this case we don't know sigma, so we will erase that sigma. We don't have sigma, and instead we replace it with s. So there's our standard error. The fourth step in our procedure, just scooch this over here, the fourth step in our procedure is that we are going to, here we go, zoom in. Fourth step in our procedure is to find the margin of error. So we got to compute the margin of error. And we do it as before by multiplying the critical value, which in this case is t sub alpha over 2, times the standard error, which is s over the square root of n. So again, step 2 times step 3. And the last step in our procedure is to actually put together the full confidence interval. So we have all the pieces we need now. Our confidence interval is just going to be x bar plus or minus m. So as we said before, oops, that should be black. It's going to be step 1 plus or minus the result from step 4. So this is our procedure for one of these problems.